Good morning. Well, we can start after this minute for wake up. Well, for me it's a pleasure stay here and present the lecture of today, which will be given by Marianne Bouchard, and well, which is also in honor of the 40 years from the first paper of Rudolf Wille. Yesterday we had the panel of Raset, and today with this lecture we would like to give also thanks to Rudolf Wille for his paper. And well, in this occasion, well, you know, many of you, Marianne is a full professor. Okay, is a full professor in computer science in the University of Montpellier from 2004. And she is also responsible of the Laboratoire d'Informatique, de Robotique et de Microélectronique de Montpellier. Mes français est notre bon. She is also president of the scientific committee of groupement de recherche in the génie de la programmation et du logiciel of the CNRS, and also member of the Mathematics, Informatique, Physics, Systems. Many chairs. So, but not only responsible of a member of a different department and so on, but also she has relevant roles in the university as responsible of, for instance, doctoral studies. And besides that, she has time for published papers. Very nice papers. She has published more than 150 papers. And from theoretical, but also very applicable papers. Indeed, she is leading different projects related to softwares, as FCA4J, RCA Bees, and what Iris, for instance. So this is an honor. She accepted the invitation here. So today she would like also to wake the concept lattice in you. Okay. So thank you very much. Again.
Good morning, everyone. First, I have to wake up the computer, yes, I think. It worked, so it should work again. Okay, so again, good morning, everyone. So many thanks for the invitation. It's an opportunity to meet a very friendly community, and it's an honor for me also to talk to you. So this is the agenda I will go through during the presentation. And first, introduction. So this time, it's the year to celebrate, as we have said yesterday and today again, celebrate. So this foundational paper from Rudolf Wille about formal concept analysis foundations. And this paper contains many notations, information, and especially some vision of this thing. And during all the past years, there was a large dissemination of the ideas along many different branches. I don't participate in all the branches. So conceptualization, philosophical developments, data analysis, knowledge engineering, classification in the meaning of information retrieval, symbolic learning, unsupervised or supervised, and tools and application, which is the branch where I am mainly these last years. And the dissemination also grew through many books, many resources, like the resource created by Jutta Pries on her webpage, and many conferences like International Conference on Conceptual Structure, ICFCA, Formal Concept Analysis, CLA, Concept Lattices and Applications, and a workshop which is 10-year-old this year, which will be which will hold in the end of July with HKI conference. And this dissemination also go through many special sessions in conferences, like this year in IPMU, the conference, the special session. And it was very interesting for me because I learned many things during the session, so it was nice. So not to give a long history about me, but to explain my positioning in front of FCA. So during my PhD, I used it to work on algorithmic problems related to partial order on a particular application which was object-oriented programming. And the problems were in the domain of class hierarchies, and they were connected to either decomposed the partial orders into blocks, into independent orders, or to produce linearization, so total orders compatible with the partial order, to solve the conflicts in multiple inheritance. And then at USLA conference, I met Robert Gaudin, and not Rudolf Villeux. I met him later in the conferences. And Robert Gaudin explained me and how the concept lattices, called Galois lattices also, were a very important structure to build some compact class hierarchies respecting some maximal factorization of properties. And this was the beginning of a journey for me, during which I did not many theoretical things, but maybe many algorithmic studies, extension to FCA for practical purposes. And as you said, yes, I'm also engaged in many applications. And I understood that, in fact, dealing with application is a complex thing. During this year, I learned that. And so I will give you today not a theoretical view on FCA, but more an engineering view on this domain. So first, I will go to through the roots of FCA. So I like this sentence of Utah, who says that formal concepts are a natural feature of information representation, which is as fundamental to hierarchies and to object attributes structure as set theory or relational algebra are for relational databases. And this is true that, in fact, we can remark that in many papers where people try to structure objects described by attributes, in fact, they use or they reinvent FCA. So I saw that many, many times. And the basics of FCA are very simple, but they are also very powerful. So I will give you just a rapid idea about all of that. So the first thing we deal with is very simple. This is just a binary relation. So you can see one here, where you can see some animals described by some properties like flies, feathered, etc. And we are interested by two dual maps. The first map, F, takes a set of objects. So for example, here we take object Silver Girl and Great Oak, and we try to collect the shared attributes, flight, feathered, etc. The reverse map J takes a set of attributes like sea habitat and its fish, and he collects the objects that share these attributes, here in blue. And a formal concept is just an association of a maximal set of objects and a maximal set of attributes. The objects are called the extent and the attributes the intent. This is vocabulary borrowed from philosophy. And here, for example, you see in red a maximal set of objects associated with a maximal set of attributes. So this is very simple. But and on this concept, what is interesting to put for class hierarchies, for example, is some partial order, and this is it can be understood like a specialization order. And for example, here, if you consider C Great Oak concept, with the extent and intent numbered by 10. So you have a set of objects. If you collect the shared attribute, you have the Y10 associated set. If you consider another maximal set of object sharing attributes, which is a C silver girl introducing concept, so you can just consider that you have an inclusion between xy and x10, and this is the basis of the partial order. So very simple things. And the concept lattice is just the set of all the concepts provided with the specialization order. So you can see it here. To read it, you have to understand simplifications. First, we show the as diagram. And the second simplification concerns the concepts. In fact, we show in the concept only the introduced object and attributes. For example, here, you see that concept 10 introduces C habitat, and it inherits all the attributes from the super concept. So you can see them here in italics. And this is the same, but dually, reversely, for objects. You see that concept 10 introduces great oak, but in fact, it represents all the objects that are introduced in the subconcept. So this is a very important thing to understand the schemas. Okay, so in fact, there is something behind which is more powerful than a binary relation. In fact, the concept lattices are the assembly of two isomorphic lattices that are the lattices of extent, could say, and the lattices of intent, ordered in a reverse way by a set inclusion. And they are associated through F and J, and F and J are just a particular case of what is called a Galois connection. And they correspond to the closed set associated to a closure operator that we can build from the Galois connection. So I won't go through all the details, except if you are interested at the end of the talk. But you can see here the definition of Galois connection. It concerns not just lattices or any sets, but any posets can be considered, X and Y. We have this pair of map F and J, and so this is not the initial definition, but just consequences. The pair Fj is a Galois connection if, when you have X below G of Y, you have in the other lattice, in the reverse schema, Y below F of X. Okay, so as I said, in fact, from F and J, you can build by composition closure operators. And with closure operators, you can have closed sets, so sets that are the same when you apply the operator. And this is something interesting in our case. When I take a set of objects, I collect the shared attributes. Then if I collect the object that share these attributes, and if I continue like that, I obtain several times the same things. It's a fixed point in the construction. Okay, so as I said, when the closed set corresponds to a lattice, so we can consider them, and we build from that the Galois lattice, which is in fact the generalized definition we can give, and we build all of that upon Galois lattices, and this is the key to have more complex construction than binary relations. And yes, and the concept lattice, I could say, it's a particular case of a Galois lattice. And this is why, in fact, in the French community, there are plenty of work that don't use the term concept lattice, but Galois lattice. So here you see some inspiring references. Of course, the seminal paper of Rudolf Villeux, the famous book by Bernard Ganter and Rudolf Villeux, which is also a reference. And you have also here some references on a book which is unfortunately in French by Barbu and Monjardin, who applied EFCA, but called Galois lattices, to the analysis of questionnaire So they work in the domain of social science. And yes, and also the roots come from Birkhoff, from Orr, and Birkhoff in the paper he published on the Galois connection mentioned that this comes from French mathematicians, Évariste Galois, who work in the domain of number theory. I'm not so strong in this domain, but so to sum up, the roots are this one. So you can consider tabular data, relational, binary relation, but you can understand that behind we have any Galois connection between finite lattices, which induces the Galois lattices. This is a very strong duality between object and attributes, or between the two lattices X and Y that you put into correspondence. And one thing which is very important, in fact, for application, from my point of view, is the fact that this is generic. If you take any lattice, you can label it to be the Galois lattice of some binary relation. And this is very important to understand that you can do what you want with that. Okay, so this was for the roots. So now, what do we have in the FCA toolbox? So we have first conceptual structure. So I show the concept lattice, which is the main and the most important one. But in fact, inside, the structure is very large, very huge. So for application, we sometimes are very limited. We can have up to 2 to the mean of size of A, size of O, so it can be large. So in many applications, we have used, and so we design many algorithms to obtain and to work with this structure, which is the suborder. This is no more a lattice, which is the suborder of concepts that introduce at least one object or one attribute. And you can understand that the number of concepts in this structure is bounded by the size of A plus the size of O. And it is very important. And in some applications, we also consider the AC poset or the OC poset, which are relevant too for some applications. Okay, so this is one of these interesting structures. And another one is the Iceberg Lattice. There are many variants of that definition. And it is the lattice which is induced by the concept with a frequent intent or frequent extent, depending what you want to make. And you see here an effect of the very interesting duality between object and attributes. And here I represented the concept lattice, the Iceberg Lattice, sorry, restricted to concept with a frequent extent. So you can see there is also a bottom element artificially added, but you can see that in the extent you have more than 50% of the object of the initial structure. Okay, also some very important things for us is the set of implication rules. So it's, I think your community knows that very well. It's just a pair of attributes that are connected by logical consequences. So all the objects of the premise that own the attribute of the premise, also own the attribute of the conclusion. And you have here some examples of implication rules that I can extract from the lattice. And there is a very abundant literature on this domain, so we use in our application some of these publications. And you can design your implication sets using different criteria, being sound, so any implication is correct, normal. Being complete, so any other implication can be deduced from your set. Being a basis, sound and complete. Having minimal cardinality. Being direct, this is also an interesting property which says that to obtain an attribute clause set, you can obtain it in just one iteration of the rule set. And also something which is difficult to manipulate is the fact that sometimes it's interesting and sometimes it's not interesting to have redundancy between the rules and inside the rules. So I cited just some author here, but there are many of us. And some very important and relevant rule sets are the minimal non-redundant set of binary implication. It is interesting because you can read it directly from the lattice. You have the basis of Duquesne-Gig. You have the left minimal direct basis of implication. You have the basis of proper premises and many others. And you have specialists in this room, so you will be able to talk with them. Okay, so here, for example, I hope it's not too small. Here you can read the Duquesne-Gig basis of implication, which is a very important basis. And you see the rules, and this is the cardinality minimal set of non-redundant implications. And if you look at the last rules, you can read, for example, here that in the two last rules, you have some equivalence between attributes, and you can see that these two equivalent attributes appear in the premise of a rule. So this sometimes is useful in application because experts want to have many information, and sometimes they want to have just the minimum of information, and they don't want redundancy. So it depends. Okay, so another very nice feature of concept lattices and other structure are the fact that you can read in the structure many things. So you can read a binary implication just by looking at the position of attributes. You can read here elytra implies fly, evident. You can read that elytra is equivalent to sex-legged because they are both introduced in a concept. So this is evident too. And there are less evident things that we use in application. For example, the extraction of mutual exclusion. For example, here, from the fact that intersection of extent of C1, C2, C3, you can deduce that you have knot of red bill and migratory and elytra, which are the attributes introduced in the upper level. And we use that, for example, in software product line engineering for variability representation. You can also read some OR constraints. This is a little bit more complex, but easy to understand. Here you have extent of C1, which is equal to the union of extent of C2, C3, C4, C5. And from that, you can read from the lattice directly the fact that the introduced attribute in C1, living being, implies the OR of the attributes that are introduced in C2, C3, C4, and C5. So you can see that here. And this is also an important thing to show when you are interested by the variability of things you are looking at. And you have, or you may have deduced that easily. You have also XOR relation. You can read, for example, here, C1 extent is partitioned exactly in C2 and C3 extent. So you can deduce living being implies warm-blooded XOR cold-blooded. Okay. So from all of that, to sum up, these very simple facts that I presented. So there is some magic triangle which gives many qualities to FCA, which is the fact that you have an equivalence between the tabular representation, or you can generalize to any Galois connection, in fact, the conceptual structure, where you can read things, you can navigate, you can do many things with them, and with some logical representation. So for example, from the Duquesne-Gig basis of implication, you can come back to the table, or you can go to the concept lattices. So this is important and very useful for us. So now, of course, you may have thought about tabular data are very simple and we cannot do many things with that. Yes, of course, in application, we don't have a binary relation, or we have, but not often. And I have to say that in the domain, people are very, very creative to address plenty of different complex data. For example, this is the historical case, the mutually valued attribute that were already addressed in the seminal paper of Villeux, and then in the book and many other works after. So here you have plenty of specialists, not only of rules, but also of fuzzy settings and possibility theory. So I put some authors. I hope, I'm afraid I forgot people, but I try to have most of them. You have also work on value taxonomies, and I use that work of Robert Godin many times in my application. We have also people that tried to build things upon logical description of objects, upon graphs. So there are different ways of addressing graph problems. And I think the most active work is by Sébastien Ferré and his co-authors, and with the approach which is called Graph FCA. We have multi-relational RCA with some extension which is defined by Stefania Boffa in the fuzzy settings, which is very interesting. We have polyadics to deal with multi-dimensional tables. We have sequences. We have temporal data, which are sometimes kind of sequences, but they have been considered separately. And we have pattern structure. So I will go with some example in that list, not all the list, because we could spend all the day with that, and maybe several days. So this was the historical multi-valued attribute dealing. So here you have, for example, a table with rent. You have a flat rented from a beginning year and an ending year. And you can understand, this is very easy to understand, that you can describe the different values by description features. So you have some different ways of representing by intervals, or I don't know, or by open intervals. And below you have the binarization of the initial table. So this is very simple, I don't comment more. So what is polyadic concept analysis? This is an interesting subfield where people try not to extract 2D concept, but they try to extract 3D concept for triadic or ND concept in the general case. So this is interesting, and you have many works that try to build the conceptual structure and also build the rules associated to these multi-dimensional relations. Pattern structure is something which is a special case because it's a kind of use of Galois connection, not the totally generalized one, but something intermediate. And in this framework, you have a set of objects, a set of description, which is the semi-lattice, and you have a similarity operation, a kind of intersection. And you can define the Galois connection by saying that the description of a set of objects is the similarity or intersection of the description. And it has been applied to many different data, for example, to intervals. So here, the similarity relation between intervals consists in using the intervals that covers both intervals that you want to generalize. For example, here, flat 2, flat 3, here are described by different ending years. And when you want to make the similarity between both, you have the ending years that goes from 2005 for flat 2 to 2011 for flat 3. So you have that. And something more difficult but very interesting is the notion of graph pattern structure, where you take G1 and G2, for example, which are description of objects, and the similarity relation consists in extracting the maximal intersection of these labeled graphs. And there is not just one, there is several. So you can imagine the complexity in terms of algorithms, yes, and in terms of results too. But this is very interesting. And a work on which we worked with several colleagues, Cyril Roum, Amin Rouanassen, myself, Amedeo Napoli, and Petko Valchev, is a relational concept analysis. So this is, as you will see, an extension of FCA. It's not a revolution, it's just an iteration of FCA. The idea is to address multi-relational data sets that are described in the form of entity relationship model. And we will try to, I will show you that, integrate the relation in the formal context as relational attributes. We have various operators that are inspired by description logics. And what is interesting in application is the fact that it's iterative process. So you can begin to build some abstraction and you can stop if you have sufficient information. And at the end, you have a set of interconnected lattice, as I will show you. So I won't go through definitions, but just through the example. So I will have an example with fleets of drones, which correspond to object attribute or formal context. You have, I will have a contains relation between fleets and drones, and I will call that object-object or relational context, and I will drones, which are from another formal context. And here you can have a look at some data. So you have some example of drones, and you have some properties like the positioning systems, avoidance systems, and information on altitude and flight time. You have here some information on fleets. So you see that the fleet are used for agriculture, rescue, audiovisual. They have architecture, different. They can have different guidance systems by human or machine learning. And you have a control strategy. And then you have this contains relation, very simple relation that says which fleet contains which type of drone. And yes, and you can see that the two fleets, rescue DF2 and DF3, do not share anything in contains. Okay, but in fact, with relational concept analysis, we will try to extract more information from these three tables. And here, what we can look at and what we can see is that if I begin by building concept of drone 14, which groups DJI Mavic Air and Unique Typhoon H Pro, they can be grouped because they share some attributes, GLONASS, avoidance system, and flight time greater than 20. Once I did that, I'm able to say, okay, there is some relation between the two rescue, DF2 and DF3, the fact that they have all their drone types inside the extent of this concept. And this is the clue to build one relational attribute, which is here for all contains in. So it means that I will be able to give this in the description of the rescue and all the fleets to say, okay, I will be able to describe both because they have all their drone in the group of drones, which is the concept 14. So this is the beginning of the things. And once I did that, I'm able to either extract new concept or complete the description of existing concept that I could have found with FTA only. And here, for example, I have this concept which is completed by this relational attribute. So we have designed for the purpose of application several quantifiers. Some are correspond to this I showed. So the fact that one object has all its links in the extent of a concept, or the object is connected to all the object of the extent of a concept, to all objects of a group, or you can have proportions, and you can imagine many, many different quantifiers. So as I said, you obtain several lattice, one per formal concept. And if you look into, you see these relational attributes that are here with the ordinary attributes. And you can apply that in the general case on any entity relationship model with the cycles. There is a convergence of the things. You can have cycles, you can have very long paths, and you may have understood that you build concepts one by one along the different iterations. So when you have a path like that, you begin by building concept on human agent. Then it can be used to build concept on human teams, and then it can be used to build concepts on security centers. So you work like that, step by step. Okay, so now with I show you the root, I show you the main things that you use in the application, I show you how we can address complex data, and now I will show you some application. So in fact there are many, and first I will review main application of FCA in knowledge discovery. I don't work on all these branches, of course. So it has been used in knowledge structuring. I will show you an example of that, not in the domain of ontologies, but in the domain of software engineering, to build or to improve data models or ontologies. In the domain of information retrieval, because we are able to navigate inside the structure, and also because of the proximity of the conceptual structure with the decision trees. And we can make many things with that. In the domain of data mining, data analysis, it has been used to extract patterns, to extract implication rules, but also association rules. There are efficient algorithms to extract association rules from the frequent concepts. You can also extract functional dependencies, which are more complex than implication rules and association rules. And you can also build measures on your data. You can make some knowledge elicitation. For example, there is a work I like, which is called attribute exploration. And behind what is that approach, it consists in taking a formal context, building the implication, proposing the implication one by one to the expert, and the expert can either validate the implication or he can say, okay, no, this is not true, and this is because my formal context doesn't contain attribute. And he gives a kind of counter example of the false implication, and like that, he will proceed and complete step by step the formal context. I think this is a very interesting approach. Okay, we also have some people that work on recommendation systems and on querying, because some interesting thing with the FCA is that you not just produce a list of answers to a question, but you produce a classified and organized list of answers. So it is very interesting, because in this organization you can see equivalent answers, for example. So there are some papers that are tried in, but they are old now. I think they should be refreshed. And so you can imagine that there are many applications in many domains: environment, linguistic, text understanding, software engineering, my branch, community, social networks too. And I will show you some of them. Okay, and we have also many tools. If you go to the page of Utah, you will find more than 50 web applications or software or plugin to other software. To have the main algorithms, to have some specific tools for RCA, for fuzzy, for Polyethic. You have search engines that are based on FCA. And you have also software which is dedicated to visualization or navigation. And there were recently 2 workshops on that theme. This shows that this is a very active branch of FCA. Okay, so now I will show you, I will make a focus on software engineering. In fact, there is also many applications in this domain. So we are too lucky for 2 things. First, because we work on data which is mostly well formatted and mostly complete, not perfect, but quite perfect. We have conceptual models, we have specification, we have source code, we have traces, we have call graphs, and we have Git actions with comments and text. And in the dots, there are many things that are text, and this is less well formatted and complete, but there is also that. And the other chance we have is the fact that software engineers are computer scientists. So they are proficient to understand, providing that we make some small training. Of course, they are not able to understand directly FCA, but with just a small training, we can make them proficient to understand and to exploit the results. And this is a chance I think we have in this domain. So they have had a large number of applications for migrating code from procedural to object-oriented paradigm, for example. These are all things. For refactoring of class models or class hierarchies. So this is also old research. I will show you results. And this can be done from artifact description or from artifact usage, and you obtain very different things. It can be used to organize, to classify software artifacts, in the past classes or components, and nowadays web services or macro services. It can be used to extract model transformation patterns in the domain of model-driven engineering. And recently, we used that for extract feature models. I will show you that in the domain of software product line. And there will be plenty of other things to do. So first, I will focus on class model refactoring. So the motivation is to have a good class model. A good class model is like an ontology, we could say, of the model we are designing for your software. And the idea is to capturing domain knowledge and to organize this knowledge around the ISO relationship, which is the skeleton of the representation. And this, in programming or in knowledge representation, encourages reuse of code or description and abstraction. So it's easier after to maintain the representation and the code. And so what we built, following the tracks of Robert Golin and Afed Midi, who did the first work, with RCA, we were able to produce something which can be called a normal form model. And the term is due to Robert Golin also. So the idea is to have the most compact structure with no redundancy inside, and in which all abstractions and all specialization relationships are included and highlighted. So I will show you on a very simple model, which is due to my colleague André Mirail, in which you can see some classes like rain gauge and anemometer, which represent a measuring device in the domain of pesticide measurement and weather. And you have classes like rainfall and wind that represent measures. And then you have roles that, and you see that there is some missing abstraction on roles because you have not the abstraction of measured something, and you have not the abstraction of device that measures something as a superclass of rain gauge and anemometer. And another missing abstraction is an abstraction of measures like rainfall and wind. And you can see that in the description because you have repeated attributes like measuring date and code quality. Some can have different types. You can see repeated code here. And you can see these two roles that are not generalized. Okay, so the idea is to identify this default in the model and to reconstruct, to refactor, to have a better design. So we have to go to the upper level, to the meta model, to have the RCA representation, and we go to this one, where you see that I will have objects that will be classes, roles, attributes, operations, and I will have meta relation between the meta classes, like the fact that a role has type and a class. So I have my meta model for RCA application. Below, don't try to look at, but below you see the different binary relation corresponding to the populated entity relationship model. Here you can see that we will build several lattices, so one lattice per meta class. So the lattice of classes, the lattice of attributes, of operations, the lattice of role, the lattice of role, attribute, and operations, yes. And if we look into, you can see here the way we will extract things. So you will see, for example, here that rainfall and wind class will share and will be generalized by a superconcept containing a reference to the attribute of which is a concept of the attribute lattice, where you can see a generalization of the two code quality attributes. And like that, by generalizing operation, by generalizing attribute, by generalizing roles, we will go and build superclasses that will generalize our classes. And what we obtain at the end, we obtain at the end a finite model which contains all the missing abstraction, printable object, measure, device measure that you can measure, measuring devices. You see that there are superclass of the initial classes, and you see, yes, in purple, many things that we have to add in UML to have a complete model that that are the trace to the initial model, which is not lost, it is just generalized. And here you have some normal form, you cannot improve it more than that. So it is now like a closed problem, so we can teach that to software engineering people to help them improving their design. And it has been designed during several theses in my team or in the team of Amedeo Napoli and Petko Valchev. It has been implemented in several tools. And there are causing methods, so maybe you know work by Lofty-Lacal or Mixikosh-Scholl or Rudensteiner, which applies the same thing in the, not with RCA, but initial FCA. And Petko, Amedeo, and Amin applied that also in ontology learning because the questions are exactly the same and you can model the things in the same way. Okay. Now I will go through another focus, maybe shorter, I don't know, because it's a recent one in which we have produced several, I think, results that deserve to be improved also. This is the domain of software product line. So this is a domain very dynamic in software engineering currently, and this is a paradigm to assist the construction of not on a single software, but on of a family of similar software. For example, in the domain of e-commerce, you produce often the same e-commerce platform. So it is interesting not to begin from the beginning each time you want a new software. And the idea is to reduce the cost, to increase the quality because you control what you produce, and to have to offer better personalization of your software too. And the main challenge in this domain is to capture variability, to be able to derive almost automatically software variants. So what we want at the end is to push a button and obtain the software. So using the model of variabilities, using base of code, and a way of assemble the different parts of the code. Okay, so in this domain, they use the several variability model, and the most used one is the feature model. You can see what is that. It's like a logical tree, and here you can read, for example, that an e-commerce software is composed mandatorily from a catalog, which can be a grid or a list, but not both. And the software can propose optionally a payment method, and optionally it can propose a credit card payment, check, or both. This is or, this is XOR, so you recognize logical operators. And these feature models are interpreted in two ways, either by the set of configuration you can build from the logical tree, or by the propositional logic formula that you can associate to this tree. So we have two interpretations, and we had two results obtained by my former PhD student, Jessie Galasso-Carbonell. The first one is that if you take any feature model, all the feature models that have the same configuration set behind, we could say also that have the same propositional logic formula. So you can map them in the concept lattice. The concept lattice contains all the logical information of this feature model, and you can reversely take the feature model, the concept lattice, take the concept lattice and then say, okay, from it, I can have a methodology to derive a feature model. So adding some information about terms, for example. So sometimes to do that, you have to have an ontology of the domain aside to help you to go from the concept lattice, which just contain logical information, to the feature model. So this is a very important result that she obtained. And the second one is that FCA is more powerful than this feature model representation because it allows, as you know, to express any propositional logic formula. So this is very important. And for example, I show you in the beginning of the talk the example of a knot of three property, not of P1 and P2 and P3, so a kind of mutual exclusion which is negated. And you cannot do that with the feature model, in a feature model. So this is a limit in expressivity of this model. But you can do that in the lattice, and so Jessie tried to show exactly what is the difference between the feature model representation and the concept lattice representation, which contains all we want to make. So application of that are many. So you can make some refactoring of feature model. So you take the feature model, you derive the configuration, and then you can come back through the concept lattice to another feature model which is maybe better organized. Or you can make the synthesis, so what exists often in the domain of software product line refactoring is that you have a set of products, so you are able to describe all the existing configuration at a certain time, and so you can from that extract the concept lattice and then extract a feature model to show to the expert of the domain. You can also make some union or intersection of feature models. For example, if you have feature models that have been designed by several separate teams, you can then reconstruct a union feature model or an intersection. So we define several such operations. And you can also, and this is very interesting, use the concept lattice to make some configuration recommendation by showing to people which sort of configuration have been used and maybe how much they have been used, and you can recommend a configuration which is close to his or her concerns. So it's very interesting. So we made also evaluation on that, on a repository which is in line, on data from Wikipedia. In Wikipedia, you have many product comparison matrices that you can use, and I think that in your community, maybe you use them also to extract fuzzy information. And yes, and we did also that in the domain of visual accessibility to be able to analyze the visual accessibility options in operating systems. Okay, and now, yes, I can take 5 minutes more. Yes. Okay, now I will make a focus outside software engineering. So this is, I'm less strong in the data domain, but I could say the FCA engineer in this topic. So I work with a colleague, Pierre Martin and Pierre Sylvie, and Priscilla Kep was our PhD student. And Pierre Martin and Pierre Sylvie work in Africa mainly to collect solutions for African farmers in the domain of agroecology. And their problem is how to find alternative solutions to chemical pesticides and antibiotics by proposing to farmers plants that have pesticides or antibiotic effect, and plants that they can find in their country mainly, so close to them. Because the idea is not to use a plane to have the plant. The idea is really a local solution to that. So they collected plenty of plant usage. They did that in scientific papers. And on top of that, they build, because Pierre Martin is also a computer scientist, they build an ontology which it can be used like an entity relationship model on this data. The data set, in fact, is just an Excel sheet, because to work with the people in Africa, it was the simplest way of communicating. So they don't have a database for this reason. They have a very huge Excel sheet, and on top of that, they design entity relationship model, an ontology, and they extract when they need to address a specific question. They extract what they want, and they have to format it to answer to the question. Okay, so I will show you. In fact, it's not good quality. I will show you a software which we recently did with other colleagues, Arnaud Salaberry and Pascal Poncelet, who are specialists in visualization of information, Émile Muller, who was the developer, Pierre Martin and myself. And the example is due to another student, Amirou Chouzerdine. And I will show you in a few slides how means making data exploration with the lattice. So here, this is local data exploration. So for example, our expert has a problem which is Aspergillus parasiticus. So this is a pest. Don't ask me more on the pest. And this is an attack on peanuts storage or in Benin, for example. And this is the question of the expert. So he has this problem and how to make that. And the idea is that often there is just empty answer. There is no answer. So what we have to make is to find alternative solution, and this is where FCA is very strong. So for example, here in the first page of the tool, so you can see the different context, the pest, the plants, the countries, etc. You can choose the pest because this is your problem. This is this bad Aspergillus parasiticus, and then you can choose it here. This show you that this is introduced by some concepts, so you dive in directly on this concept in the lattice, and you can see the concept introducing the pest. And you can be interested by the shared attribute. If you are interested by knowing which is the controlling plant, you are going to concept 10. The controlling plant is Aspilia africana. Nice. But you can say, okay, but where can I find Aspilia africana? So you can follow a possess link. And unfortunately, you are going to Nigeria, so this is not a solution to your problem. So you can come back to concept 10 to find some alternative to Aspilia africana. So what you do often with the lattices is going down or going up or going down to find cousin concept, because they will often offer you alternative solution. So here you can go up to concept 20 and go down and finding another plant, Chromolena odorata, and you can be interested to know what is controlled by this plant and where you can find it. So first you can find it in Benin. You see that by continuing your navigation. And you can also see that Chromolena odorata controls Aspergillus ocraceus. So this is not parasiticus, but this is a cousin pest. And you can deliver to the expert not a solution, but an hypothesis, and they can work on that. And they know that there is a possibility, a conjecture, that Chromolena odorata could control Aspergillus parasiticus, and as the farmer will find that in Benin, this could be a solution for him. Okay, so this is what you do when you navigate, and you avoid with the lattice. This is very strong result. With the lattice, you avoid to go to empty solution. In fact, you go from possibility to another possibility, and this is very important. Okay, so of course, challenges here are many. First, the tool is not totally finished. And then other challenges are that now we have incomplete and imprecise data. So I listen many things these days, and I think I will come back with many ideas to improve our approaches, maybe with some fuzzy settings. We have potential mistakes, like in many data sets. And the other problem is that at the moment, even for navigating in the lattices, we need a data scientist, because the tools are still difficult to understand by domain experts. For us, it's easy to understand what is the object, but for them, it's really complicated. And one thing that Pierre Martin thinks now, he says that maybe rules are more easy to understand by experts than this. Okay, so now I will conclude shortly. I hope you understood the message is that FCA is like a Swiss knife for knowledge discovery. It should not be used alone, so it is interesting to work with FCA with many other settings, and it can be used for many tasks. For example, for navigating, for building models, for extracting rules, patterns, etc. And of course, there are many different avenues for future research. I should have put another item first, which is visions, because first, I think there are philosophical messages behind FCA. This is not my domain, I'm not strong at that, but I see that many people have many ways of thinking FCA which are very inspiring. From the theoretical point of view, there are many things to make, of course, and in particular, not working on FCA in isolation from the other knowledge discovery approaches. I think this is a very important thing. We have algorithms to design, to have local and incremental construction, using maybe distributed parallel algorithms. We have to make many things, this is for me, in the methodological part. For example, to improve user interaction, to use FCA for other tasks like detecting and correcting anomalies. We begin to work on that. To classify patterns and rules, and be able to generalize from specific application to common methodologies that could be applied to other domains. Of course, addressing complex data is not finished. Address big data is not finished, and we could say that FCA maybe is not for big data. In fact, the strength of FCA is more on complex than on big data. People are beginning to say that FCA or CA are good tools also to measure data complexity. I see that Amedeo Napoli began to work on that domain. I'm not strong also on that, but I saw papers by Tom Anika, by Sebastian Rudolph, maybe Francisco also, on the construction of hybrid AR-CAD systems, including FCA and other solutions. And it can be a way to produce partly and maybe modestly explainable things. And also, as people in application part, we are very interested by integrating all of this in a data science workflow. For example, this is a matter of fact that you cannot find any FCA algorithms in Orange or in scikit-learn. So this is a pity, and we should fight against that. And of course, once we have the tools, we can also use them in a Jupyter Notebook, for example, to make just data science workflow using many things, including FCA. Okay, so thank you. Many thanks again.
Thank you very much. Now we have time for questions.
Thank you very much for the very interesting talk. in relation to this future work that you mentioned, do you know of any attempts to combine it with deep learning or something? Because that seems to be a natural idea, because many problems here are NP hard, so deep learning probably is the right approach.
Yes, so there are work on that. I'm not specialist, as I said, so I saw that, so Tomanica published a paper where he defined something which is called FCA2-VEC. Okay. And the idea is to, I will try to explain that clearly. The idea is to, using the concept lattice as a way of giving a context to objects and attributes, in fact, and to make some embeddings. Then I see that some people tried to use FCA, for example, to understand results. So once you have classified, not in the sense of organization, but in classes, then you can be interested by explaining what means the different classes and how you can describe them. And then it's interesting to go to the symbolic word to make that. And maybe, Francisco, you want to add things? Because yes. Yes, Francisco is more a specialist than me.
So we're actually working at the intersection of FCA and predictive data analysis, but FCA is mainly, and for the time being, an exploratory data analysis technique. So if you pay heed to what Tuki said, that you have to do first exploratory data analysis to prepare for your predictive data analysis, and then carry out predictive data analysis, FCA should be like a part of finding representations for vectorial spaces and stuff like this. But some of us also think, especially the people doing fuzzy FCA or FCA in a fuzzy setting and other algebraic structures, that you can actually do predictive data analysis. So we're working on restricted Boltzmann machines that are predictive generative machines, very primitive, but very much related to formal contexts. And you can get, as Marianne said, some idea of what's inside the machine once you look at it in the FCA way.
Thank you, Francisco.
Thank you. Well, more questions, comments? Well, meanwhile, Dominique?
Thank you very much for a very interesting talk. At the beginning, you mentioned that concept lattices can be quite large for complex data sets. On the other hand, they are very powerful tool for visualization to see what happens inside. So my question is, what is your opinion? Is there a possibility to produce some kinds of simplified concept lattices which are not 100% accurate with respect to the data, because then they would be very complicated, but maybe they are simplified, maybe they highlight the most important patterns, dependencies in the data?
Yes, so I come back to slides from the beginning. Maybe I was too rapid on that. I think it is, it was before. So yes, so in the first of all, I mainly use not lattices. I remember it was, I think, in Clermont-Ferrand at ICFCA 2007. There were many mathematicians from Germany, including, I think, maybe Rudolf and Bernard Ganter. And you were there? 2005? Maybe. And I remember we presented things with the EOC set. I don't know if you remember. And it was really complicated for us. They say, but why you don't use concept lattices? It's a beautiful structure. I don't remember exactly their arguments, but our argument was exactly this is first to reduce complexity. Second, because from the AOC poset, you can reconstruct the lattice. You can use the AOC poset and add some relevant concept, not introducer concept, but useful concept. So you can be between the concept lattice and the AOC poset. And this structure, first, is linear in the size of a number of attributes, a number of objects. And the fact that it introduces many things is very useful and often sufficient. It doesn't contain all the intersections, but for example, in the domain of software product line, we even don't use AOC poset, we use the AC poset. So just the concept introducing the attributes, because this is sufficient, plus the information on extent to go to a feature model, for example. So this is sufficient. So this is first that. So yes, I remember this year, it was, we came back saying, maybe we did a mistake. Anyway, it's difficult to explain to some mathematicians that posets are interesting too. And for me, it was evident that posets were interesting because I worked all the time with posets. And yes, and the second part was that was the Iceberg Lattice. So maybe I was too quick on that slide. So this is a family of lattices. So this time these are lattices. You can just add some bottom or top if needed, and they contain the concept either with a frequent intent or frequent extent, not both. So you can build many of them depending what you want. And this is from them that you can also, for example, extract as frequent items or things like that. So I think this was your question. And here, this is again the word of lattices, so
well,
it's okay.
I would like to add something. Is
you add it because you're going to. I think you are going to add that one, right?
Yeah.
You can actually. There are two indiscernibility relationships between objects and attributes, and you can weaken the indiscernibility on attributes, and immediately your lattice becomes simpler.
Yeah, it's another mechanism as a threshold and so on, but we must take into account that the whole concept lattice is not recurrent in many applications, as we can compute a base of attribute implications from which you can generate more information. So sometimes it's not required to build all. This is also one of my questions, because when you are using your software and looking for in the concept, it is possible to obtain this similar or the same result using attribute implications.
What do you mean?
In the slide in which you present RCA bis,
yes.
You are looking for inside the concept.
Yes, maybe I will launch the video. I don't know if it will help, but maybe it could help to understand. This is the same that in CLA. You don't learn anything. Yes, so here I choose things. Yes, and so then after choosing that, we navigate from concept to concept. And your question is to navigate between implications or to...
Yeah, if the consequences you obtain navigating through the concept is possible for obtaining the last result. It is possible to obtain this information using attribute implication, for instance?
In fact, I don't know, but but this is exactly the question of Pierre Martin.
Okay.
Because Pierre says that this is nice for people that do FCA, this kind of software, but this is not nice at all for experts in the domain. And Pierre say me, no, for the other Pierre Sylvie, I cannot show him that. I only can be able to show implication. And in fact, we are. So we don't want to deduce implication from that. The idea is more, now we are designing with Arnaud Salaberry and Pascal Poncelet another visualization software which will be used to visualize implications and to navigate between the implications. This is not exactly your question, but it's yes, it's a way of saying yes, implications are useful. In fact, yes.
Okay, okay.
And to finish to answer to the question, something that we didn't mention but we used to work with is the fact also that in the lattice there are some particular elements which are the irreducible elements from which we can reconstruct also things, and it can be also a solution to simplify, to reduce the not the lattice, of course, but to reduce the representation, and we use reduced tables, for example, when we build the implications. So we first clarify and reduce the formal context, then we compute the implication, and then we reconstruct the implication we should have obtained with the initial formal context. So yes, so in fact it's a really relevant question to simplify things, yes.
Thank you. Some have time, what, a couple of minutes or some question, comment? So, yeah, André?
I have a question related to the and by analogy, nearest neighbor classifiers. Maybe if you have, for example, new case, you subtract a neighborhood of this for this case, so you can consider only a small part of the object, and you can consider a small lattice related to these objects. Is this something what can be done in this approach or not?
Okay, so sorry, it was difficult to. You understood or no?
No.
No.
Sorry.
Can you repeat, please?
Yes. So we have this well-known KNN method in machine learning. So if we have a new object, we are selecting from already known objects a neighborhood of objects, and we base the classification of these objects on the basis of this neighborhood. So in this case, instead of considering the huge lattice, I can consider a subset and the lattice related to this subset. And maybe this analysis can be much simplified.
Yes.
Is something done in this direction, or?
Yes, in fact, I think I understood your question. Yes, in fact, when we work in FCA, either you can select part of our data set, and then we can build things like inside that and classify inside that. Or yes, we can consider, I don't do that at the moment, but I saw paper on that, people that extract sub-formal concept, in fact, and work with that. So then you do things in a simplified context. You have a simplified classification. Is what
really.
It's called lazy classification, that we are not building this very huge lattice in advance,
yes.
But when we have a new case, we are building this small lattice related to this new case, and we can analyze.
You want to say adding object one by one? Yes.
When I have a new case, and I would like to say something about this new case, so I do not need to have this huge lattice for all cases, but I would like to have a small lattice related to this case. And next to analyze these properties will be much easier. So
yes.
Well,
I think there are approaches for that, yes.
Yeah, well, indeed, the paper in which was pricing the Poland society, Dominic said yesterday, is in this direction. We apply rough set in formal content analysis in order to group objects with similar attributes, and then we apply to reduce, and then we have this philosophy given by rough set, no? Grouping object with similar attributes, they exist classes, and then apply FCA. Well, we haven't time for more questions, so thank you very much.
Thank you.
It's a pleasure to be here.